So the majority of trans fatty acids, okay, found in the diet result from hydrogenation. Hydrogenation means adding hydrogen across a double bond. That's a reaction used to convert oils into solid fats, like margarine. Okay, oils are healthy for the body. They're liquids, they flow easily. Virgin olive oil is very good for the body. We turn it into stuff that is unhealthy for the body because it tastes better. We take our oils and our liquids, and we turn them into margarines and fats because it tastes better to us. Okay, we have a taste to it. So we convert it by hydrogenation into these trans fatty acids versus the cis fatty acids. Okay, so trans fatty acids, they elevate the bad LDL cholesterol and lower the good HDL cholesterol. So it increases the risk of heart disease. So trans fatty acids, what they fry the French fries in, ice creams, things like that, those are your trans fatty acids. Okay, they increase the risk of heart disease. They also show that trans fatty acids increase the risk of type 2 diabetes. Okay. You have what's called cis fatty acids, which means at the double bond, where you can see the double bond, these are on both sides of the double bond. Okay. Fatty acids are long-chain carboxylic acids found in vegetable oils, unsaturated fats, and animal fat. Okay, animal fats are saturated fats. That's I'm not supposed to say fat, it's supposed to say fat. Okay, naturally occurring fatty acids like olive oil is a cis fatty acid. Okay, that's your cis configuration. Both the same things on both sides of the same double bond. Trans fatty acids. You can see one opposite side to a double bond. Okay, that's your trans fatty acids. Okay, there's no natural source of trans fatty acids. We make those. Okay, we make them in a laboratory, so it tastes better to us. And it tastes better for us, but it is unhealthy. Okay, the majority of trans fatty acids result from hydrogenation reactions. We make it by adding hydrogen across a double bond. Okay, trans fatty acids, like I said, lower levels of good cholesterol, raise the levels of bad cholesterol, and increase heart disease. So we create trans fatty acids in the lab for food products. So each of the following pair of molecules identify the cis isomer and the trans isomer and name each one. Okay. Okay, the one on the left, cis or trans or neither. Who wants to guess?
The one on the left is cis.
Perfect. The one on the left is cis. The one on the right is trans. Okay. Cis and trans. Cis means same side of the double bond. Trans means opposite sides of the double bond. And then name the compounds. Okay, what's the longest carbon chain? 6 carbons, right? So it's going to be hexene. This one's going to be a hexene because the double bond. And you have double, what position is double bond at? 1, 2, 3, 4, 5, or 6?
3.
Got 3. So you have cis 3-hexene and trans 3-hexene. Next one. Okay. First of all, one on the left is cis or trans. Either cis or trans or cannot have a cis or trans. So it could be neither.
Trans.
One on the left is trans. Okay. Opposite sides of double bond. The one on the right is going to be cis then. Same size of double bond. Trans and cis. Okay. So you have trans 2,3-dibromo 2-butene. Okay. So working backwards again, ENE means there's a double bond. Butene means there's 4 carbons. At the number 2 carbon, there's a double bond. There's 1, 2, 3, 4. There's bromine groups, and there's 2 of them. It says dibromo at the numbers 2 and 3 position. Okay, and it's a trans relationship. So the name tells us everything about the compound. And the other one is going to be cis 2,3-dibromo 2-butene. Okay. Which of the following molecules can exist as both cis and trans isomers? Draw the cis trans isomers and name them if they can. So we have A, B, and C. Let's do them individually. There's A. All right. Can A exist as a cis trans isomer?
No.
Perfect. You got it. It cannot. Why?
The two on the right are the same.
Perfect. Exactly right. The two groups here attached to the bond, the ethyl groups are exactly the same. Anytime there's the exact same thing attached to either carbon of the double bond, this one or this one, there cannot be cis trans isomers. Can't happen. Because no matter how you switch these in rotation, it's still gonna be the same thing. Okay. So let's name this thing. So you don't have to put a cis or trans in front of it. We have, let's pick our way. 1, 2, 3, 4, 5, 6 carbons. So it's going to be hex, and it's going to be E and E double bond, E and E because there's a double bond. The double bond's at the number 3 position, and we have 1 chlorine attached at the number 3 position also. Okay, so to name this thing would be 3-chloro-3-hexene. Okay, there's no cis trans isomer, but the name is still 3-chloro. I'm sorry, I left out the ethyl group. There's an ethyl group at number 4. If we did, this was our double bond here. This is our longest carbon chain. So there's 2 attachments, chlorine and an ethyl group. So 3-chloro, 4-ethyl, 3-hexene. All right, we won't drop it this time. Are cis trans isomers possible again?
No.
No, perfect. Because you see, there's 2 bromines attached to this carbon, 2 identical groups. So you cannot have a cis trans isomer. So let's name our compound. So we're going to run the longest carbon chain, 1. And we start there because that'll give our double bond the lowest possible number, and also our substituent in this case, 2, 3, 4. So these are what's added onto the chain. So how would you name this? This would be butene, right? And where's the double bond at? What number? Carbon.
1.
Number 1, so it'll be 1-butene. And there's 3 attachments to it. There's 3 bromo groups. So it's tri-bromo because there's 3 bromine groups attached. And what numbers are they at?
1, 1, 2.
1, 1, 2. So 1, 1, 2, tribromo. So 1, 1, 2, tribromo, 1-butene. 1, 1, 2, tribromo, 1-butene. Okay, and this is number C, letter C. Can C have cis trans isomers?
Yes.
Yep, because you have 2 methyl groups and 2 chloro groups. They can be on the same side or they can be on opposite sides. So the one over here is cis because the chlorine groups or the methyl groups, either one you choose, are on the same side of double bond. Okay, opposite sides of the double bond is trans. Cis is same side, trans is opposite side. Okay, so we have a cis and a trans, and we have 4 carbons in our longest carbon chain. So we have number 1, number 2, number 3, and number 4. Okay, so there's your chain. And we have double bond at number 2, right? And 4 carbons. So it's 2-butene. And then we have substituents attached. We have chlorine groups, right? How many chlorine groups do we have attached?
2.
2.
2, right. So it's going to be dichloral. And what numbers are they at?
2 and 3.
And 3. You got it. So this compound over here on the left-hand side is going to be cis 2,3-dichloral 2-butene. Cis and trans. So cis 2,3-dichloral 2-butene. And then trans 2,3-dichloral 2-butene. Okay. Draw a condensed and structural forms for each of the following compounds. Cis 3-octene. Okay. What I'll do is draw the line form in the top, and then underneath it, we'll do the condensed and structural formulas. So octene has how many carbons?
8.
8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 carbons. Octene means there's a double bond at the number 3 position. So 1, 2, 3. And this happens to be trans because it's going up. Okay. So the condensed formula is going to be CH3, CH2. Let's do the structural first, be easier for you to see. Okay, let's do the structural formula. Okay, so you have 8 carbons. Right? You make your 8 carbon chain. Okay. And it says there's your ene. And it says at number 3, there's a double bond. And it's going to be in the cis position. So that means there's 3 hydrogens here, 2 here, 1 here, 1 here. I want cis. Let's go up 1 here on the same side, double bond. Hydrogens, 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 hydrogens. Okay, so there's a hydrogen at the end of every one of those lines. Does that make sense so far?
Yeah.
Okay, perfect. So we got on 8 people. Okay, so now draw the condensed formula. We just say CH3, CH2, CH double bond. I just copy exactly from the top. CH, CH2, 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 CH3. And there's your condensed formula. So you should be able to write the condensed formula, the structure formula, and the line formula. Okay. There's your structure formula. And you can see it's a cis configuration. Okay, the alkyl groups are on the top, hydrogens are on the bottom. Okay. 8 carbons, number 3 has a double bond, like the formula says. And then there's your condensed form, just like we had. Okay. It's easy to draw the structure one first, and then draw your condensed formula, because then you can see where the hydrogens are going. Trans 5-chloro-2-hexene. Like I said, easiest way to do it is just draw so you can see it. Draw the structure formula. Hex means how many carbons?
6.
6. So I would draw just up here, put 6 carbons. 3, 4, 5, 6. That's how I'd start it. And then the E and E means there's a double bond, right? At the number 2 carbon. So right there, there's a double bond. And at number 5, there's a chlorine group. 1, 2, 3, 4, 5, which is a Cl group. And it tells you it's a trans relationship. So let's put our hydrogens on. Every carbon has to have 4, right? So far this carbon has 1. 2, 3. Now it has 4 bonds. This carbon has 1, 2, 3. It's got to have another one. This carbon has 3. It needs another one. It says it's trans across the double bond. This has to have 4. This already has 3, so it needs a 4th. And then 3 carbons there. Okay. So now all you got to do is look at your height, look at your sticks you drew. So the first carbon has 3 sticks, 3 hydrogens. The second one has 1. So CH, double bond, CH. There's only 1 hydrogen there. Okay. The next one has CH2. I don't need to put the line there. CH, CH2, CH, parentheses Cl, remember, because this refers back to there in the parentheses, CHCl, and then CH3. So from the structure formula you drew, you can easily do the kinetic formula or the line formula. Okay, so there's your structural formula laid out in, shows you the trans configuration. Okay. Again, working backwards, this is a number 2 carbon. 2, 3, 4, 5, 6. Okay, we always do a double bond, the lowest possible number. So I'm numbering left to right. Okay. And at number 2, there's a double bond. And at number 5, there's a chlorine. And it's a trans relationship. The hydrogens are opposite sides here, and the alkyl groups, okay, are on opposite sides also. So there's your structural formula. Your condensed formulas, like just like we wrote above. You can read a little clearer when I print it out. CH3, CH double bond. And remember, when we put parentheses, it goes backwards to this carbon. So it shows you the chlorine is attached to the number 5 carbon, because there's only 6 carbons in it. That making sense? So far, so good?
Yeah.
All right, perfect. Trans 2,3-dichloro-2-butene. Again, let's work backwards. Butene means what? How many carbons?
4.
4 carbons. So put 4 carbons on a chain. There's your structural formula. Okay. The E and E means what?
Double bonded.
Double bonded at number 2. Remember, A and E is single bonds, E and E is double bonds, Y and E is triple bonds. Okay. And it says at numbers 2 and 3, there's chlorine groups. And they're going to be in a trans relationship. So 2 and 3, there's chlorine groups. That's it. And fill it in with hydrogen. This one needs 3. This one needs 1. This one doesn't need any. And this one needs 3. Just make sure every carbon has 4 bonds. That's how you fill the amount of hydrogen. That's enough hydrogen put in there. So if you want to write it out, you see the first carbon is CH3. You see the second carbon is CHCl. So CH, and then put parentheses Cl, because it goes to that carbon. Then there's a double bond. Oh, I did something wrong. I made a mistake. Someone should have caught me.
Yeah, the second carbon doesn't need the hydrogen.
That's not there. It already has 4 bonds. So you're right, does not need the hydrogen. So it's CH3. Okay, because carbon can only have 4 bonds. It can't have less than 4, can't have more than 4. Remember the Lewis structure for carbon is 4 electrons. So it can only have 4 bonds to it. So CH3, C, Cl, double bond C, Cl, CH3. Okay. So there's your structure formula, a little clearer than when you print it out. Okay, you can see the trans relationship. We have chlorine at number 2 and number 3, and we have 4 carbons with a double bond at number 2. And like we did the form writing it out, it's CH3, CCl, and you can put parentheses around the chlorines if you want to. Most people do that just to refer back to the carbon, but you don't have to. It's not mandatory. Especially when there's no confusion. There's only 1 chlorine there. Okay. And that's your condensed formula. Okay. Name needs to come in the IUPAC system. All right. Be sure to indicate cis or trans where applicable. Okay. So how many carbons? What's our longest carbon chain, I should say?
4.
Okay, 4 carbons. So this is going to be bute, and there's 1 double bond, so E and E. And where's the double bond at? Which carbon number?
2.
Carbon number 2, so 2-butene. Are we going to label this from left to right or right to left? Or does it matter?
I don't believe it matters.
If you look at the double bond, it makes no difference which way you go. Okay, we can either go left to right or right to left. But if you look at the substituent, since it doesn't matter for the double bond, then we drop down to the substituent. So which way to number it, we get the substituent the lowest possible number.
Right to left.
Perfect. So it has to be right to left in this case, because that substituent's added. You go the double bond first, and you give that the lowest number. Then if that's a tie, you go to the substituent. So 1, 2, 3, 4. So it's 2-butene, and we have a, what group do we have attached here? What's this group called?
Methyl.
Methyl, 1 carbon. So it's 2-methyl. Okay, so put this name together. Is cis-trans possible?
No.
No, because there's 2 identical groups attached here on the right-hand side. So we put this together, it's 2-methyl, 2-butene. Okay, so 2-methyl, 2-butene. Again, no cis-trans isomers are possible with this compound. Okay. Let's look at this one here. Is a cis-trans isomer possible?
Yes.
Yes, it is. Because we have 2 exact things that we can compare. If we can compare those, then they can be up or down. So this can be, is this going to be cis or trans?
Cis.
This is going to be cis. Right. Our longest carbon chain is 1, 2, 3, 4, 5, 6 carbons. So what's that make it?
Hexane.
Hexene, E and E, double bond.
Hexene, sorry.
That's it. That's perfect. No problem. So hexene. And are we going to count left to right or right to left?
Left to right.
Left to right. Perfect. The double bond doesn't matter. Double bond's at number 3, no matter which way you count. So that's a tie. So then we drop down to the next level we're going to determine. And that's our substituent. And we have a methyl group attached. Okay? And that is counted lowest if we start on the left-hand side. Now put this carbon as number 3. So it'd be 1, 2, 3, 4, 5, 6. Okay, so it's 3-hexene. That's where double bond is, and it's 3-methyl. Okay, so putting this whole thing together, we have cis, 3-methyl, 3-hexene. And that's the IUPAC name of the compound. I had a question yesterday of if the IUPAC is a certain formula. IUPAC is just a naming system. There's no formula or anything to it. We have all the rules we follow, but there's no real formula for it. But it's the International Union of Applied something chemistry. I keep forgetting the name of it. Okay, so IUPAC is just a naming system. Okay, here's another one. Now, is cis-trans possible? And if it is this cis or trans or neither?
It's trans.
It's trans, perfect. It's trans. Okay. What's our longest carbon chain that's connected?
6.
6, so it's a hex. And there's a double bond, so it's an E and E. And are we going to count from right to left or left to right?
Left to right.
Left to right's perfect. Okay, because you give the double bond the lowest possible number. And then if it's a tie, then you go to constituent groups. But there's no tie in this case. The lowest possible number is starting left to right. Good, that number 2, 3, 4, 5, and that's 6. Okay, so it's a 2-hexene. And there's substituent groups here and here. What are those substituent groups?
5,5-dimethyl.
Perfect. Exactly right. It's dimethyl, like just like you said, dimethyl. And they're at number 5. And there's 2 of them there, 5,5-dimethyl. So name this thing total would be trans 5,5-dimethyl 2-hexene. Trans 5,5-dimethyl 2-hexene. All right, alkenes in nature. Alkenes are very abundant in nature. Ethene, okay, 2 carbons, double bond between them, ripens fruit and promotes plant growth. Polyenes, built from the isoprene skeleton, are called isoprenes. These polyenes are alkenes with multiple double bonds. So this isoprene unit is used over and over again in styrofoam, in different polyetherins that we build, in synthetic compounds. This unit repeats itself over and over with multiple double bonds. And that's what forms a lot of our products. Okay. Isoprenoids. Okay. Geranol and D-limonene are some smells. Roses and geraniums. Okay. This is the compound. Again, you're looking at 2 double bonds in the compound. So those are alkenes. So that's geranyl. Okay. That gives you the rose smell. D-limonene smells like oil of lemons and oranges. And yet you see multiple double bonds. Okay. These are natural occurring compounds. Mycene, okay, is oil of bayberry. Okay, farnesol is like lilies of the valley. Okay, that one has 3 double bonds, and so it's the top one too. Have 3 double bonds in the compound, and you can see how they're either cis or trans. Okay, so you have lots of reactions involving alkenes and alkynes. We're going over the different types of reactions. We talked about hydrogen, a hydration reaction, which is adding hydrogen. Okay, so the key reaction alkenes are 2 molecules combined to give a new molecule. You have 4 different types of reactions of alkenes and alkynes. You have hydrogenation reaction, which is adding hydrogen. That's what we did with the for the cis to trans fatty acids. So hydrogenation means to add hydrogen. Halogenation means to add a halogen. A halogen is fluorine, chlorine, bromine, iodine. That's one of the halogens. So hydrogenation is adding hydrogen. Halogenation is adding hydrogen. Is adding halogen, I'm sorry. So hydrogenation is hydrogen being added. Okay, halogenation is a halogen being added. Chlorine, bromine, fluorine, iodine. Hydration is adding water. You hydrate it. Hydrohalogenation, okay, is an H and a halogen, okay? The addition of a hydrogen halide molecule like HCl, HBr, HI, HF. So it's a hydrohalogenation, okay? Everybody sees the 4 different terms and how they're different, because we're going to have all 4 of those reactions and how they react across a double bond. Okay, so hydrogenation, halogenation, hydration, and hydrohalogenation. We give examples of all 4. Okay, general addition reactions. Okay, addition reactions, okay, are when you're adding 2 things across a double bond. So here's your double bond. Okay, and these are R groups, which just means there's attachments to it. And now you're going to open this double bond up. Okay, and you're going to add A, and you're going to add B to the 2 carbons, resulting in a single bond. So you open the double bond up, you're sharing the electrons in the double bond with this compound here. And you're adding one side to one carbon, other side to another carbon. That's just a general addition reaction. You're adding across a double bond. Okay. Remember the reactions we did with alkanes. Oh, remember that? Remember we had, let's do an example here, then I'll erase it. C, and these are all hydrogens, plus chlorine with light. Okay. Remember those reactions we had in chapter 10? Okay. With those were not addition reactions because you're not adding it. You're opening that chlorine bond and you're replacing one of these carbons, one of these hydrogens with the chlorine. That's chlorine, hydrogens plus HCl. Okay. Remember, those are not addition. Those are substitution reactions. You're substituting one hydrogen for a chlorine. Okay. When you have a double bond, these are addition reactions. You're adding both compounds, both elements here across that double bond. We're not substituting one for the other anymore. Substitution is what we did when we had single bonds, alkanes. Addition reactions we do when we have a double bond. Did that make sense?
Yes.
Okay, perfect. Let me get rid of some of this. I don't know if I have to or not. Okay, so these are addition reactions. Here we go, get rid of all that. Oh, it's getting rid of a lot of it. So a small molecule, AB, reacts with the pi electrons of the double bond. Remember, there's sigma bonds, which form your single bond, and the pi electrons are the ones in the p orbital. Remember sp-df orbitals? The pi bonds are in the p orbitals that extend above the double bond that lock it into place. So these pi electrons in this double bond are opening up and reacting with and sharing for an addition reaction. Okay, so the pi bond breaks. That's the bond above the sigma bond, opens up, and the electrons are used to bond the A and B pieces. So you're adding both pieces, not adding just one. I'm thirsty. All right. So some additions require a catalyst, like light or heat or acid, something like that can be done. Remember the definition of catalyst? There's 2 things a catalyst does. One of them is speeds up a chemical reaction. The second thing a catalyst does is it gets regenerated. It's not used up in the reaction. It can be reused. Okay. There's different types of addition reactions. One type is symmetrical, where the same atom added to each carbon. It's symmetrical. Hydrogenation, you're adding H2. You're going to add an H and an H to each carbon. Halogenation, bromine, Br2, Cl2. You can add 2 bromines, 1 to each side. You can add 2 chlorines, 1 to each side. Those are symmetrical. They're the same thing being added to both sides of the double bond. Okay, unsymmetrical. Unsymmetrical means there's an H and another atom that are added, like hydrohalogenations, HCl. One side gets H, one side gets chlorine. HBr, one side gets H, one side gets bromine. Okay, those are not unsymmetrical because there's different elements being added to different sides of the double bond. Then you have hydration reaction. This is water. One side gets H, one side gets OH. Right? So you're adding two different things. That's why it's unsymmetrical. Remember, water is H2O. You break it apart into H plus, OH minus. Okay, so one carbon gets a hydrogen, one carbon gets an OH group. Okay, that's what's called unsymmetrical. Okay, when you do that, when you do hydration reactions, you have to have a strong acid catalyst. Okay, sulfuric acid, battery acid, H2SO4, it's a strong acid. Phosphoric acid, H3PO4. That's the acid. How many people go to the dentist and they do the white fillings and they put that blue stuff on your tooth? That blue stuff is hydrophoric acid. Okay, it's 35%. It etches the tooth, gets ready so the bonds can adhere. You put the composite filling in. Right, that's a strong acid. It etches tooth structure. And then you got self-addition. Okay, or polymerization, where one unit gets linked over and over and over, like polyurethane, styrofoam, things like that. Those are self-addition reactions where the whole unit just gets linked over and over, makes a long chain. So those are all addition reactions. You need to understand the difference between those three: symmetrical, unsymmetrical, and self-addition or polymerization. Okay. Any questions of those three? That's what we're going to start doing right now, is start doing those reactions. Okay. Hydrogenation. Look for the key word in it. Look for the word hydrogen. Okay. We're adding hydrogen across a double bond. Hydrogenation. So there's your compound. We're adding hydrogen across double bonds. We had hydrogen to one side and hydrogen the other side as this double bond opens up. And one of the electrons goes to each side and adds to the hydrogen. It requires platinum, palladium, or nickel as a catalyst with heat and pressure for this reaction to occur. So this hydrogen attacks this double bond opens up and transfers the electrons, so you can get two hydrogen bonds. That's hydrogenation. Okay, so hydrogenation is the addition of a molecule of hydrogen, H2, to a carbon-carbon double bond to produce an alkane. So you have an alkene as a product, alkene as a reactant, I'm sorry. You have an alkene as your reactant, and it ends up with an alkane as your product. Okay, the carbon-carbon double bond is broken, and the hydrogen-hydrogen single bond is broken, and they're reformed to give you the alkane that you just saw. The new carbon-hydrogen bonds are formed. Okay. Like I said, platinum, palladium, or nickel is required as a catalyst, along with the addition of heat and pressure for this reaction to occur. Okay, that's hydrogenation. Oh, you saw this, it went backwards again. We have the same thing there. All right, write equation of the hydrogen of alkenes. Okay, linoleic acid, cis 912 octadecadienoic acid is an essential fatty acid. Okay. This means we must obtain it from the diet. It's of an essential fatty acid. It means our body has to have it, and our body cannot make it. So we have to find it in nature. Remember we said we see cis. Okay. Cis fatty acids are found in nature and are healthy. They're oils usually. We convert those to trans to make them unhealthy because they taste better to our mouths. They feel better. Because it's better to put something solid in your mouth like margarine. It tastes better than putting oil on your bread rather than butter. Okay. So essential fatty acids means you must get it in your diet. We have to consume it. You cannot make it. It is found abundant in sunflowers, safflowers, corn oil, which are often hydrogenated to produce margarine. Okay. Write a balanced equation. So the hydrogenation of linoleic acid. All right, so you have, how many double bonds do you have in linoleic acid?
Two.
2, perfect. Octa, let's pull it apart. This is an oic acid. So it means it's a benzoic acid. We haven't done that yet, but we will. That just means it's an acid, okay? And it says diene. Diene, E-N-E, E-N, the E-N, the E's been dropped, but E-N-E is double bond. Di means 2. And it's at the number 9 and the number 12 position. Octadeca means 18 carbons. Octa is 8, deca is 10. So 18 carbons. At the number 9 carbon, there's a double bond. At the number 12 carbon, there's a double bond. And they're both in the cis position. You just broken down the whole word right now. You know what it means. Okay, so we got 2 double bonds. If we have 2 double bonds, okay, how much hydrogen are we going to need to do it? Remember, hydrogen to H2. So how many hydrogen molecules do we need to hydrogenate linoleic acid?
4.
You need 4 hydrogens. Okay, so you need 2 H2 molecules because one will hydrogenate one double bond, one will hydrogenate the other double bond. Remember, hydrogen is always diatomic. Okay, there are 2 double bonds, like we said. We'll need 2 molecules of hydrogen for every molecule of linoleic acid that is hydrogenated. Okay, remember H2 splits on one double bond, get you an alkane. Go another double bond, give you an alkane. Okay, so this is linoleic acid. If you want to count the hydrogen, I count the carbons, there's 18. And this is at number 9. Again, so you have 1, 2, 3, 4, 5. Oh, I'm going wrong. I'm going backwards. Hold on. Let me erase that. Okay, this is a number 1 carbon. We haven't got there yet, but we will with carboxylic acids. We start at what's called the carbonyl group, which is a double bond oxygen. This is a carboxylic acid. So there's 1, 2, 3, 4, 5, 6, 7, 8. Remember 9, 10, 11, and 12. Remember at 9 and 12, there were double bonds and they're both cis. So it shows you at 9 and 12, there's both cis and both double bonds, and there's 18 carbons total. So that's linoleic acid, okay? Plus 2 hydrogen molecules. Remember, 1 hydrogen molecule goes here, and the other hydrogen molecule goes here to hydrogenate and get rid of that double bond. Okay, and it produces stearic acid. So there's your balanced equation. Okay, you got linoleic acid plus 2H2 goes to stearic acid. Stearic acid still has 18 carbons. Okay, now the double bonds are gone. So what happens now is you have these long chains like this. So now these molecules can stick together. Okay, these double bonds here were breaking up that pattern. So you don't have the London dispersion, of course, don't hold them together. So when you hydrogenate something, you make it saturated. It has the most hydrogens now. Now it starts to stick together. You get butter, you get margarine, things that tend to stick together rather than the oil. This is what clogs your arteries because it sticks. Causing arteriosclerosis. That's why the hydrogenated fats are bad for you. They cause heart disease and all kinds of other things because now these things get in your bloodstream, the stearic acid, and it sticks together. Okay, and that's what clogs your arteries. Whereas up here in linoleic acid, you had the double bonds, which created a break in the chain, so you didn't get those long chains that could stick together anymore with the London dispersion forces. Okay, so we've converted something that's healthy to something that's unhealthy because people want to feel something when they taste it. Okay, and that's your balanced chemical equation. right there. Okay, so liquid linoleic acid is converted to stearic acid, which is a rather hard solid. Okay, so in margarine production today, partially hydrogenation is generally used because it produces a fat that can be more readily spread as a better mouth feel. So we make margarine by only partially hydrogenating, so you can spread it out so it's not as solid. Okay, because it feels better when you can eat it. They may add to add butter flavoring, milk solids, salt, an emulsifying agent, preservatives, vitamin A for nutrition value, and a bit of beta carotene for color. So they add all kinds of things to this linoleic acid. This is olive oil that you used to have. Okay. Write a balanced equation for each of the hydrogen alkenes. Hydrogenation means what? Break that word apart. What does hydrogenation mean? Let's see who's paying attention.
Add water.
Not water,
Oh, hydrogen.
hydrogen. Hydrogen, look for the words inside the name. Hydrogenation, adding hydrogen to it. Okay. Cis-2-pentene. First thing to draw it out is draw cis-2-pentene. E means what?
That there's a double bond.
Perfect. There's a double bond. Pentene means how many carbons?
5.
5 carbons. At the number 2 carbon, there's your double bond. And cis means same or different? Which one?
Same.
Same. Perfect. Same side. So there's pentene, 5 carbons. The number 2 carbon has your double bond, and it's a cis relationship. Okay, so we're going to add hydrogen. Hydrogen is H2. Where's the hydrogen going to attack?
Double
It goes
bond.
after, perfect. It goes after the double bond. The reason it goes after the double bond is there's a high concentration of electrons there. Okay. In the alkane, there's not a high concentration of electrons. In the pi bond, there's those extra electrons on the outside of that sigma bond, and those are available to attack. And that's what the hydrogen attacks. So this double bond opens up, just like that. And one hydrogen goes here, and one hydrogen goes here. Okay. Is the product going to be cis or trans now? It's a trick question. Do you think the product's going to be cis or trans?
Is it
No.
neither?
Perfect. Who said, you said what? You said neither, right?
Yeah, neither.
Neither. Exactly right. It can't be because it's going to be a single bond. You got to have a double bond for it. You got to have a double bond or a ring, a cyclical compound for cis trans isomerism to occur. The product's going to be all single bonds. There's not going to be a double bond because you're going to have CH3, right? And then hydrogen was here, and this carbon, CH3. Then we add a hydrogen, hydrogen, CH2, CH3, and hydrogen. We'll write it better when we do this part here. So we're adding hydrogen, and then we come out with our product, which is CH3 bonded to CH2, bonded to CH2, bonded to CH2, bonded to CH3. This double bond here has now become a single bond because you've added a hydrogen on this side and a hydrogen on this side. So now you get CH2, CH2, and then the CH2 up here, that gives you 3 CH2 groups and CH around the end. Okay, that's hydrogenation. Okay, hydrogenation. You're adding hydrogen to a double bond. So cis-2-pentene becomes, what's the name of this structure? 5 carbons, all single bonds.
Pentane.
Pentane, perfect. So cis-2 pentene, the product formed is pentane from hydrogenation. You're adding hydrogen. Pentane, perfect. Trans-2 pentene, again, it's going to be the same thing, right? There's your structure. You're going to add hydrogen to this bond, a hydrogen to this bond, this carbon, I'm sorry, and this bond opens up. Okay, and you end up with pentane again. Same reaction, doesn't matter if it's cis or trans. Okay, you're adding hydrogen across a double bond. 3-hexene. So let's just draw it. Carbons. Okay. There's a double bond in the number 3 position. So it's going to be plus H2 because only one double bond. This double bond opens up. 2, 3, 4, 5. And gets a hydrogen here and a hydrogen here. Okay. Because all these are hydrogens here, right? And now all this becomes hydrogen. Okay, so 3-hexene becomes, there's your double bond, opens up, and now you get your CH2s in there. Becomes hexane. Okay, it becomes an alkane. Just because you're adding hydrogen across a double bond, hydrogenation. Propene. Okay. What's the product going to be from propene?
Propane.
Propane. Perfect. Just adding hydrogen across that double bond. There's propene. There's your CH2, CH3, and you're adding it right across that double bond. And it becomes propane. So the trans isomer 2-pentene was used in the problem. Would the result be any different if the cis isomers was used? So here's the trans, and this is what we ended up with. Okay. Would the result be the same if we use the cis isomer? Yes or no?
Yes.
Yes, perfect. It would be the exact same. It would make no difference because all you're doing is making it into single bonds. The real in pentane. Okay. Pentane has no double bonds. No cis trans isomers are possible. You got it. Okay. Right. Balance equation of hydrogenation of 1-butene and cis-2 butene. Okay. So there's 1-butene. 1-butene is 4 carbons. Double bond at number 1. So there's a hydrogen, 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 hydrogens, hydrogens. Okay, so we attack this double bond here. We get rid of this top bond and we add a hydrogen and a hydrogen. So what does 1-butene plus H2 become? What's the name of this thing?
Butane.
Butane. Okay. So this is 1-butene. Okay. Plus H2, and it becomes butane. You have the name there too. Yep. All right. Is there any, can you make a cis trans isomer with 1-butene?
No.
Perfect, because right there, same thing attached to one of the carbons. So 1-butene reacts with hydrogen becomes butane. Cis-2 butene. Okay, double bonds in number 2 position. Okay, if I add hydrogen, What does this become? CH3, then you got CH2 because I added a hydrogen, CH2, CH3. So what's the product? What's the name of this thing? Yeah, butane, perfect. Okay, and it becomes butane. So if I had one butene or cis-2 butene, the product is exactly the same. So any compound, no matter where you put the double bond, if you're going to add hydrogen, it's become the exact same thing. Just getting rid of the double bond to make the exact same product, no matter where that double bond is in that compound. Okay. The conditions for hydrogenation of alkynes is very similar to those for hydrogenation of alkenes. What would you think the difference is going to be? In other words, if we had a double bond and had to add hydrogen, if we had a triple bond and had to add hydrogen, what would you think the difference is? Okay, in this one, how many hydrogen atoms do I have to get rid of the multiple bond? I have to add one, right? If I have a triple bond, how many hydrogen molecules do I have to add now?
2.
2, 1 for each bond. One H2 goes to this bond, one H2 goes to the other bond to make it to a single bond. So the difference between alkenes and alkynes is in alkynes, you're going to have to add double the amount of hydrogen because you have a second double bond, a multiple bond. So in alkenes, you have one multiple bond. Alkynes, you have 2 multiple bonds within between the carbons. There's supposed to be a carbon here. Okay. So 2 moles of hydrogen added the triple bond of alkyne to produce an alkane. Okay. So here's your triple bond. So now you have to add this hydrogen here and here, and then this hydrogen here and here. So I need 2 moles of hydrogen because of the triple bond. That's the difference. It still takes platinum, palladium, or nickel, and still has your heat or pressure for it to go. So that's an alkyne, and it converts to an alkane. It just takes double the amount. Okay, so write balanced equation to complete hydrogenation of each of the following alkynes and name the products and reactants. Okay, so name everything. And you want complete. Complete means it goes all the way to an alkane. You're not stopping halfway. You're not stopping at an alkene. Okay, so what are we going to add to this? Plus, again, complete hydrogenation. So hydrogenation, we're adding hydrogen. How many molecules of H2 are we going to need to take that triple bond and go all the way to a single bond?
Two.
2, perfect. We're gonna have to have 2, 1 for each of the bonds in there to get to a single bond. Okay. If I had 2 triple bonds in one compound, I would need 4. I need 2 for each triple bond. Okay. So plus 2H2, and it's going to end up as CH3, right? And then we're going to add a hydrogen. We have 2 hydrogens to each carbon. So CH2, CH2, CH3. So name the starting compound and name the product. What's the name of our starting compound?
Butane.
Okay, 1, 2, 3, 4 by time. What's the number?
2.
2, perfect. Starting compound is 2 butane. What's the product formed?
Butane.
Butane, perfect. Okay, so 2 hydrogens goes to butane. Again, that's 2 butane, and it goes to, we convert it to butane by complete hydrogenation. second one. Let me get some of these marks out of the way so you can see it. Okay, so this is a compound now. How many molecules of H2 am I going to need for complete hydrogenation of B? Plus how many H2s?
Two.
2, perfect, same as before, right? We're gonna need 2. Okay, so here's the reaction. It's 2 hydrogens. Here's our product. Here's our reactant. What's the name of the reactant? Five carbons,
Pentane.
triple bond. Pent what?
Pentane.
Pentyne, right? A Y in the ending. Because this is going to be a triple bond. And it's 5 carbons and it's a number 2. So it should be 2-pentyne. Okay. Triple bond, 5 carbons, the bond's at the number 2 carbon. Okay. And the name of the product is pentane, all single bonds. Because we had a hydrogen twice across that bond. We got rid of the triple bond, got to go into a double bond. Got rid of the double bond, we go into a single bond by adding hydrogen across the multiple bond. So hydrogenation is used in the food industry to produce margarine, which we talked about. It's a mixture of hydrogenated vegetable oils. Okay, so vegetable oils are unsaturated, which means they have multiple bonds because there's more ways to add hydrogen to it. That's what, remember, unsaturated means it does not have the full amount of hydrogen that it could possibly have if everything was single bonds. So vegetable oils like canola oil and stuff like that all have multiple bonds. They contain many double bonds. As a result, they have very low melting points and they're liquids at room temperature. And they're healthy for you. They get absorbed by your bloodstream into your blood, and it does not cause arteriosclerosis. It does not cause hardening of your arteries because they're liquids. They're not solids. Hydrogenation of these double bonds to single bonds increases the melting point of these oils and results in fats like Crisco that remain solid at room temperature. Okay. Conversion of a typical oil to fat involves hydrogenation. Okay. The next example is triolanine is an oil converted to tristerin, which is a fat. Okay. This is your triolanine. This is a triglyceride. Okay. And you see this long double chain, and it has multiple double bond inside the chain. Okay. So this is an oil. It's a liquid at room temperature. Gets absorbed by the body when you eat it. Stays a liquid in the blood. Okay, because it doesn't stick together. We're going to add 3 hydrogens. Why are we adding 3 H2 molecules? Because there's 3 double bonds. 1 H2 for every double bond has to adhere to it. Okay. And this is the product. Okay. This is tristerin, which is a fat now. Okay. There's no multiple bonds. Okay. In these long chain hydrocarbons. Okay. So now this becomes a solid at room temperature because they start to stick together. They have the long chains are not broken up by multiple bonds. So this is unsaturated. This now becomes saturated. Okay. Saturated fats are much worse for you than unsaturated fats. And it's just hydrogenation. You're adding hydrogen across the carbon-carbon double bond. Okay. So you're taking unsaturated, going to saturated. So halogenation. Okay. Hydrogenation is adding hydrogen. Halogenation is adding a hydrogen. So now instead of adding two hydrogens, we're going to add 2 chlorines or 2 iodines, or 2 bromines, or 2 fluorines. Can I get rid of that? No, guess not. All right. So here's your alkene, your double bond. X represents a halogen. Fluorine, chlorine, bromine, iodine. One of those. Those are your halogens. And you're going to add a halogen to each side of the double bond. So you have an alkene, your halogen. So you have an alkyl dihalide. Alkyl is carbon compound. Di means 2. Halide means a halogen. Okay. So halogenation, again, halogen, okay, is the addition of a molecule of a halogen, which is represented as X2, to be carbon-carbon, to a carbon-carbon double bond to produce an alkane with 2 halogens attached to it as substituents. Again, the double bond is broken. The new carbon halogen bond results. Reaction occurs Weyrelli, does not require a catalyst. Remember when we did hydrogenation, adding hydrogen, we had to have platinum, palladium, or nickel as a catalyst, and then heat and pressure to help that go along. So this one does not need a catalyst. Chlorine and bromide, okay, are the most often the halogen added. So let's take an example. That's an example. So 1 pentene, there's your double bond, 5 carbons plus bromine. It attacks the double bond, opens up the double bond, and adds bromine to each of those carbons. Okay. So you've gone from 1 pentene plus bromine to 1,2-dibromopentane, which is an alkane. So we went from alkene to an alkane. Okay. You're adding bromine just like adding hydrogen, exact same thing. Okay, except this time you're adding bromine or chlorine, whatever the halogen is. So this is a colorless solution when it's 1 pentene. Bromine is adding red. Okay, and as the reaction proceeds, it becomes colorless again. So you can tell if your compound you're trying to identify has a double bond by adding bromine to it. If it stays red, there's no double bond for it to attack. If it goes back to clear after you add bromine, then there was a double bond. Okay, so the bromination reaction can be used to show the presence of a double or triple bond in an organic compound. The reaction mixture is red because of the presence of dissolved bromine. So the only thing that's red is this. So if bromine's not used up, it's going to stay red. If bromine gets used up, the solution goes back to clear. So if your solution is clear, it means you had a double or triple bond. If the solution is red, it means you did not have a double or triple bond. Okay, because it didn't react. Okay, so if the red color is lost, the bromine has been consumed. Bromination has occurred and the compound must have a carbon-carbon double or triple bond to it. The greater the amount of bromine that must be added to the reaction, the more unsaturated the compound is. Okay, with the more double bonds or multiple bonds you're going to have. So a diene or an alkyne would take up twice as much bromine as an alkene with a single double bond, because you have to add 2 more bromines to that double bond, take twice as much. Okay, well, this is what it looks like. This is bromine in this container. Here's your compound in the glass. Okay, you add bromine here and it stays red. That means the hydrocarbon did not have a double or triple bond. We added bromine and it turned back clear. That means the double bond reacted with the bromine. So the compound in the beaker had a double or triple bond. So the left beaker contains bromine, but no unsaturated hydrocarbon. Okay? It means the hydrocarbon did not have a double or triple bond. The right beaker contains bromine, but it has an unsaturated hydrocarbon, okay? Which is colorless, which means it reacted to produce an alkane with bromine. Okay, an unsaturated hydrocarbon. That had to be to start with, because you had to have this one here, the clear one, had to have a double bond or triple bond for the bromine to attack, or else it would have stayed red also. Write a balanced equation showing the chlorination of 1-pentene. Okay, first of all, you have to know what 1-pentene is. How many carbons in 1-pentene?
5.
5, perfect. So you have 5 carbons. At 1 carbon, there's a double bond. And then there's hydrogens. We'll draw the hydrogens this time. Okay, chlorination means you're adding chlorine. So plus Cl2. And the chlorine attacks this double bond, opens it up, and adds a chlorine at each of those carbons. So you get, let's take away this double bond and add a chlorine and a chlorine. And that's what you get as your product. Okay. So this is pentene, 1-pentene. There's your double bond. You add chlorine. The double bond used to be right there. At each carbon of the double bond, you have added a chlorine molecule. So you've gone from 1-pentene. What's the name of the product? Who wants to guess?
1,2-dichloropentane.
Perfect. 1,2-dichloropentane. So you started with 1-pentene, pentane. 1,2-dichloropentane. You've gone from an alkene to an alkane, and you got a chlorine across the double bond. Okay. Bromination of trans-2-butene. So here's trans-2-butene. Okay, double bonds at number 2. You attack this double bond with bromine. So you put at where there was a double bonds at number 2, you've added a bromine across it. And it's 2,3-dibromobutane. Okay. Would it have mattered if I started with cis-2-butene? Would that have made a difference in the product? Yes or no?
No.
No. Because there's no bond, there's no cis-trans isomer in the product. It's all single bonds. So if I started with cis-2-butene, I would have ended up with the exact same product. Okay. Right, balance equation for the complete chlorination of each of the following alkenes. So 2,4-hexadiene. Okay. Diene means how many double bonds?
2.
It means 2, perfect. And hexa means 6 carbons. So you have 6 carbons with 2 double bonds at numbers 2 and number 4. So we have 6 carbons, 2. We have double bond at 2 and a double bond at 4. So complete chlorination means chlorination of all multiple bonds. Okay. So this is going to be plus how many hydrogens? How many hydrogen molecules do we need for complete, no need hydrogen, no need any. Answer should have been 0. Is a trick question. Complete chlorination. So how many chlorine molecules do we need to completely add enough chlorine to get rid of all the double bonds in that compound?
2.
Perfect, 2. Plus 2 Cl2s, and it's going to go to, we're going to get rid of this double bond and add chlorine here and a chlorine here. We're gonna get rid of this double bond, add chlorine here and chlorine here. So that's what we're gonna get. We're gonna get rid of both the double bonds, and at both the double bonds, we're gonna add a chlorine to each carbon where the double bond was attached. Is that making sense? The same thing we did with hydrogen, except instead of hydrogen now, we got chlorine. So we have still got 1, 2, 3, 4, 5, 6 carbons still. Okay. So we started with 2,4-hexadiene, added 2 chlorines, and we produced, what's the name of the product we produced? We produced 2, 3, 4, 5 tetrachlorohexane. 2, 3, 4, 5 tetrachlorohexane. Hexa 6, A and E is all double bonds. Tetrachloral means 4 chlorines. Tetra is 4, and they're at number 2, at number 3, at number 4, at number 5. Does that make sense?
Yes.
All right, perfect. 1,5-dibromo-2-pentene. Okay, let's do, I'll do a line structure for change. Pentene is 5 carbons, 1, 2, 3, 4, 5 carbons. And it's 1,5-dibromo, so at 1 and at 5, we have a bromine. Okay, and at number 2, we have a double bond. And we're gonna have chlorine, and we're gonna need 1 CO2 because we only have 1 double bond. So we're gonna have 1, 2, 3, 4, 5. We have a bromine. We have a bromine. And at each of these, we're gonna have a chlorine. Okay, and there's your line structure doing it that way. Okay. And doing it this way here, we have our bromines, which are attached, and we've added a chlorine. This is our double bond right here. So at our double bond, we're going to add a chlorine. And it only needs 1 chlorine to only have 1 double bond. We need 2 for 2 double bonds, 3 for 3 double bonds, and so on. Okay, so we have 1 double bond. We need 1 molecule of chlorine. The chlorine goes to each one. So here's our bromine attached. Here's our CHCl, and it's we have it twice. Here's our there's CHCl, CHCl, CH2Br. Okay. So who wants to name the product? We're starting with 1,5-dibromopentane. Who wants to name the product for me?
One 5-dibromo 2,3-dichloropentane.
Perfect. Exactly right. There's 1,5-dibromo. The bromides stay the same. The chlorines are going to be at 2 and 3, so 2,3-dichloro, and it's 5 carbons, pentane. 1,5-dibromo, 2,3-dichloro, pentane. That's how the answers will be on your exams. We've got to work it out and then give me the right answer that way. Most of your answers will be in that way. And there was a mistake with chapter 10 quiz. It asked the same question 5 times. I changed it so there's 5 different questions now, because if you answered it wrong, you missed the whole thing. So those who took it and got it wrong, I reset it so you have another chance to take it. Okay, but if you had trouble with it, let me know. But if you got a score of 5 on, I left it for you because I figured it was my mistake. I don't know how it did that, but I did fix it. It's brought to my attention. But that is fixed now. But if you have questions like that or anything comes up funny, let me know and I'll fix them. All right. Complete chlorination, balanced equation of each alkane. So 2,3-dimethyl butene. So we have butene is 4 carbons. 1 butene means double bond in the position. 2,3-dimethyl. 2,3-dimethyl. And that's it. And we open up this double bond and we're going to add Cl and Cl. So plus CO2. So we need to add 1 CO2 because we have 1 double bond. Okay. That's what the condensed formulas look like. Here's your double bond. Remember, whenever there's parentheses, it means what's in parentheses refers back to the previous carbon. Okay. And there's our line structure. There's our condensed formula for it. Okay, so 1 chlorine goes to and adds the chlorine across the double bond. Everything else stays the same. So we've added this chlorine here, and we've added this chlorine here. Okay, so we end up with 1,2-dichloral. We added again right across the double bond. Number 1 and number 2 carbons each got a chlorine. So 1,2-dichloral, and the methyl groups stay the same. They don't move. 2,3-dimethyl butane instead of butene because it's a single bond now. It's saturated. Okay, 4,6-dimethyl 2-heptene. Again, let's draw our line. So heptene is 7 carbons. 7 carbons. 4,6. There's number 4. There's number 6. Those are your dimethyl groups. And number 2, there's a double bond. Okay. So we're going to add chlorine. We attack that double bond. We open it up. This I'll just erase it. And this was an end. This was an end or double bond. And we've added chlorine. Okay. If you want to name that thing, there's 2,3-dichloral. So this is 2,3-dichloral, 4,6-dimethyl heptane. Okay, here's what the answer is. So 2,3-dichloral, 4,6-dimethyl heptane. Again, this 2 goes away because that was our indication where our double bond was located. We don't have a double bond anymore. Okay. So that's why that 2 is no longer in the products. Okay, addition of bromine. Okay, take this plus bromine. How many bromines do we need? How many molecules of bromines do we need for complete bromination of the following of that alkane of propene? 1 propene.
Just the 1.
Just the 1. Perfect. So it's going to add on each side of the double bond and attack the bond, open it up, use those pi electrons. So propene plus 1 bromine goes to, okay, 1,2-dibromo propane. So 1 propene goes to 1,2-dibromo propane. Again, break each name down. Tells you exactly what it is. Okay. So our double bonds are getting a halogen attack to them or a hydrogen attack so far. And these are symmetrical reactions. Asymmetrical can be a little bit different. Addition of bromine to the following alkane also. Okay. Okay. So this compound, Nc plus bromine, and we only need 1 because only 1 double bond. Okay. And it goes to, there's your CH3. Your CH of the double bond is going to add a bromine. Your CH, the double bond, is going to add another bromine. And then you have CH3. Okay. So you have 2,3-dibromo butane. And what was the name of this was 2-butene. Okay, there's your reaction. Remember you added the 2 bromines to the CH groups. And this is 2-butene. And the other one was 2,3-dibromobutane. Okay. So alkynes also react with halogens, bromine or chlorine. Amounts to alkyne. Remember, now there's a triple bond. So if there's a triple bond, we have to have double the amount because the first reaction uses the pi electrons to get rid of the triple bond. And I have a double bond. The second reaction uses the pi electrons, a double bond, to make it into a single bond. Okay, so we need double the amount of halogens for a triple bond versus a double bond. And it's going to produce a tetrahaloalkane. Alkane is all single bonds. Halo is a halogen, and there's going to be tetra, which means there's going to be 4 of them now instead of 2. Okay, so here's your triple bond. Okay, the first bonds open up, and you get an X and an X. That gives you a double bond. Double bond opens up, so you get an X and an X, and that's what you get here. That's what you get for each multiple bond. The first set adds across, then the second set adds across. So an alkyne halogen goes to an alkene, and it takes double the amount it does for a double bond because it is a triple bond. It's an alkyne. Okay, so here's your alkyne. So what's going to happen is a chlorination. You're going to open up that triple bond. So CH2 now. Double bond. Okay, drawn nice. CH2. Why am I doing CH2? All right, CH3 is right there. There's your triple bond. We're going to open up, make a double bond. C. I'm forgetting to add the halogen. Okay. Start back. CH3C, and you're going to add the halogen, which is chlorine, Cl. Double bond C, Cl, CH3. That's the first step. You've added a chlorine across each side of the double bond. The next step, you're going to add a chlorine across the other one to get rid of the double bond, make a single bond. CH3, C, Cl twice. C, Cl twice. CH3. That's the next step. Now it's a single bond. Okay, so you've taken this bond plus 2 chlorines to make this all alkanes. It's one step, then the next step. You open up the triple bond, make it a double bond by adding 2 halogens. Take the double bond, open it up, make it a single bond by adding 2 more halogens. So you're adding a tetrachlorine to it in this case. So we've gone from, this is 2-butene. We've added 2 moles of chlorine to go to 2,3-dichloral, 2,2,3,3 tetrachloral butane. So there's 2-butene. So 2,2,3,3 tetrachloral butane. There's 4 chlorines, and then there were 2 and 3 positions. That's where the double bond was. All right, complete chlorination. So we're going to take this triple bond and attack it. Open it up, add 2 chlorines, make it a double bond. Open the double bond up, add 2 chlorines, make it a single bond. So our product's going to be 1, 2, 3, 4, 5 carbons, so it's pentane. So it's going to be 2,2,3,3 tetrachloral pentane is going to be the product. You added 2 chlorines for each bond, each multiple bond. And you started off with 2-pentyne, which is your triple bond. You added 2 chlorine molecules to it to give you, what did we say it was? We said it was 2,2,3,3 tetrachloral pentane. 2,2,3,3 tetrachloral pentane. Okay. All right. Everybody understand hydrogenation and halogenation? Now it's a symmetrical addition. What's that? Okay. It's a symmetrical addition. Hydration is not a symmetrical addition. Now we're getting into a little bit more tricky stuff because we can have two different ways of adding it because it's not the same depending which side you add it to. Hydration means adding water plus H2O. So we're going to add H to one side, OH to another side. Okay, so here's your compound. Okay, you're adding water in the presence of acid. Okay, you're adding an H and an OH. Now, if you look at that, we're adding two different things. So if these R's are different, then there's two different compounds we could make. We could have the OH here and the H here, or the H here and the OH there, depending where it adds. And there's rules that we're going to learn that will tell us which product to be made most often. Okay, so you have to understand the difference between symmetrical addition versus unsymmetrical addition. In unsymmetrical addition, there's a possibility that two or more products could be formed because of the addition, because of the way they attack the double bond, which position they take. Okay, so water molecule can be added to an alkene. The hydration of water molecule to an alkene is called hydration. Okay, presence of a strong acid is required as a catalyst. Okay, the resulting product is an alcohol. Alcohol means there's an OH group attached. That's what alcohol means. We've had R groups. We've had, when the functional group is an OH, then we produce an alcohol. We haven't learned how to name alcohols yet, but we will. That's in the next chapter. I think it's the next chapter. All right. So the following equation. So it's a hydration of ethene to produce ethanol. Ethanol is drinking alcohol. That's vodka, scotch, rum. That's all. That's what's in your drink to make it alcoholic is ethanol. Okay. So we take ethene and we turn it into ethanol. Okay. This is ethene. Ethene is 2 carbons, 1 double bond. It's not one ethane because there's no other, you can't put the bond except for right there. So that's ethene. You're adding water. So we're opening up this double bond. Same thing. We're attacking that double bond. We're opening it up and we're adding H and OH to it and getting rid of the double bond. Okay. That's hydration. Now, does it matter if the OH is written over here? Would that make a difference if I switch those? Would it be the same compound or a different compound? Anybody want to guess? Is anybody still here?
It would be the same.
Be exact same, perfect. Exactly the same, because you just switch that around 3-dimensional space. Okay, so that, let me put it back again. That'd be the exact same compound. Okay, whether I wrote the OH here and the H here would make no difference. Okay, perfect. So under symmetrical, now if the sets were different, okay, we'd have different products. So 2 products are possible depending on how the 2 groups are added to the ends of the pi bond. Okay, if it's not a symmetrical molecule, it's going to be an unsymmetrical addition. Hydrogen will add to 1 carbon, the OH will add to the other carbon. That's what makes it unsymmetrical. So hydration, there's an H and an OH. Hydrohalogenation, there's an H and a halogen. So either we're going to add OH and H, or we're going to have Cl and H, or Br and H. Okay, those are your unsymmetrical additions. There's 2 types: hydration and hydrohalogenation. All right, here's our first example. Okay, look at the difference. This is what we're starting with. We're going to attack that double bond. Okay, we can either add the OH to the left side and the H to the right side of it, of the double bond. Or we can have the H to the left side and the OH to the right side. So when there's because it's asymmetrical, it's not the same around around the double bond. There's a CH3 and an H. The other one has an H and an H. Okay, so it makes a difference. Okay, so there's two products going to be formed. Which one is going to be the more prevalent? It's going to be a major and a minor product, or it's going to be the same, 50-50. It all depends on the conformation of it. Okay, so you went from propene, one propene, just propene, to the major product, which is 2-propanol OLs alcohol. We haven't learned that yet, but we will. 2-propanol or 1-propanol. Okay, this is your minor product. This is your major product. 2-propanol is major. 1-propanol or propanol is minor. It's rubbing alcohol. Okay, the rule is hydrogen likes hydrogen. That's the rule. In this case, this hydrogen has two other hydrogens connected to the same carbon. In this one, this hydrogen has one other hydrogen connected to the same carbon. Hydrogen likes to be where there's more hydrogen because there's less inhibits that way. So the more hydrogen there is, the more the hydrogen likes to attach to it. So this is going to be the major product. This is going to be the minor product because this one has more hydrogen attached to the carbon that the other hydrogen is adding to. Does that make sense?
Yes.
Perfect. Okay. And it's called Martinovol's observation. But it's a lot easier for me to say hydrogen likes hydrogen. And I can remember it a lot better. But Martinovol's observation is that hydrogen, the major product formed in an unsymmetrical addition reaction. The hydrogen is going to go to the carbon that has the most hydrogen attached. And that's going to be the major product. The other one's going to be the minor product. Now, if both carbons have the same amount of hydrogen attached, then it's going to be 50-50. There's going to be no difference behind because they have the same amount of hydrogen attached. That's Martinovol's principle. Okay. But it's just so much easier to remember hydrogen likes hydrogen. Okay. So during Martinovol's observed many acid addition reactions to carbon-carbon systems. He noticed the majority of hydrogen went to a specific end of the double bond. It goes to the end of the double bond that has the most hydrogen attached. He formulated an explanation. Okay. So this is his rule. When an acid adds to a double bond, the hydrogen of the acid most often goes to the end of the double bond, which has more hydrogens attached initially. So the one that has the most hydrogen attached in the reactant is where the other hydrogen is going to go. Okay. Remember, water is an acid, HOH. Remember, hydrochloric acid, HCl, HBr, hydrobromic acid. Okay, H and OH. H and Cl. The hydrogen here is going to go to where the most hydrogen is going to attack the carbon of the double bond, which has the most hydrogen attached more frequently. So that's going to be, it's going to still have a minor product, but that's going to be your major product. HBr, same way. All right. So let's give an example. Write the equations of all products for the hydration of the unsymmetrical alkene 1-pentene. Okay, 1-pentene is 5 carbon. I'll put up here so it won't get in the way. Oh, I can't even draw a carbon atom anymore. 1, 2, 3, 4, 5, right? And it's 1-pentene, so there's a double bond there. So there's hydrogen hydrogen, 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 hydrogen. Okay, so when we attack this double bond, come in there, and it's going to be a hydration reaction. You're going to have an H and an OH. Okay, on the carbon on the left of the double bond, there's two hydrogen attached. On the carbon on the right of the double bond, there's one hydrogen attached. So is the left or right, when is hydrogen going to go to the left or right carbon most of the time? Which one?
Left.
Left. Perfect. That's all the rule says. That's it. Long fancy name, all this fancy stuff. That's all it says. Look at the carbon that has the most hydrogen. That's where the most hydrogen is going to be. So you're going to have a major product when hydrogen bonds to this one, and you have a minor product when hydrogen bonds to that one. That's it. That's all unsymmetrical means. You have two different types. You got to be able to determine them. Okay. So here is 1-pentene. Oops, why am I not drawing that? Okay. And here's our double bond. And we got water for hydration reaction, which means H and OH. So the OH is going to go to the left-hand side here, and the hydrogen is going to the right-hand side here. The OH can go to the right-hand side here, and the H on the side here. So we just switch sides. We put one to each side. Now we need to determine which one's the major product, what's the minor product. Okay, is the top major or minor? What's it going to be? Remember, hydrogen likes to go where
Top is
hydrogens are
major.
attached. What's that?
Top is major.
Perfect. You got it. That's exactly right. The top is major. That's your major product because here's these other two hydrogen here. This is where this hydrogen attaches to. Hydrogen likes other hydrogens to be attached to the same carbon. And so this hydrogen, there's two. This hydrogen, there's one. Two is greater than one last time I checked. So the major product is going to be 2-pentanol. OL means there's an OH group on it at the number 2 position. That's how you name an alcohol itself. And the minor product is going to be pentanol, 1-pentanol, where the OH group is on the number 1 carbon. Okay? That's all there is to unsymmetrical reactions. Write a balanced equation of hydration of each of the following alkenes. 1-butene. Okay? So 1-butene is 4 carbons. With 1 double bond. And there's where you're going to attack, right here. Hydration means H and OH. Okay, so there's a hydrogen here, 1 hydrogen here, 2 here, 3 there. Okay, so as you open that double bond, H is going to go to one side, OH is going to go to the other side. Okay, so we're going to open up our double bond right here. We're going to attack that. The OH goes to the left, H goes to the right, OH goes to the right, H goes to the left. 2 different types. That's what's going to attack the double bond. Okay, H and OH, and they're going to switch places. That's all. One's going to be major, one's going to be minor, unless they're exactly the same. So is the top one your major or your minor product?
Major.
Major, exactly, because there's 2 hydrogens right here versus only 1 hydrogen right there. See? And the rules, Markovnikov principle says hydrogen likes hydrogen. It likes to be on a carbon where there's the most hydrogen possible. And to name this thing, we're getting ahead of ourselves, but there's 4 carbons and the OH group is on the number 2 carbon. That's like a substituent group. So it's 2-butanol. Okay. 2-butanol. OL means it's an alcohol, means OH. Butane is 4 carbons. AN is single bonds. And the OH group is at the number 2 position. So it's the same we've been dealing with it. We just haven't gotten into that, which we will get into. Getting a little advanced notice here. Okay. That's your major product. Your minor product is 1-butanol or butanol. Okay. Because here hydrogen is bonded to the carbon that only has one other hydrogen. It likes to be where there's more hydrogen. So it does that a majority of the time. So you have a major product and you have a minor product. Okay, so it's a little more complicated than symmetrical addition reactions where you have just H and H, you know, two hydrogenations, or you have two chlorines and two bromines or whatever. Okay. All right. Okay, 2-methyl-3-hexene. Okay, so you got to know what you're dealing with. You're dealing with 6 carbons. Okay, there's a methyl group at number 2. And at number 3, there's a hexene, a double bond. Okay. So there's our compound, and we're going to add H and OH to it. And we're going to add one H to the left, OH to the right. Then we're going to switch and add OH to the left and H to the right, because there's 2 chances of it going across, right? So here's our compound drawn out, nice and neat, 2-methyl-3-hexene. And here's our double bond, and that's what we're going to attack. And we use H and OH. Okay, in one place, H goes to the left, OH goes to the right. OH goes to the left, H goes to the right. So we switch them. Okay, is the top one. Okay, look at the top one there. Is the top one going to be the major or the minor product?
Is it 50-50?
It's 50-50. It's exactly the same. If the hydrogen bonds here, there's one hydrogen. If the hydrogen bonds here, there's one hydrogen. It's exactly the same. So it doesn't matter which one it bonds to. So if it doesn't matter, it's going to go 50% of the time. You get 50% of 5-methyl-3-hexanol, and you get 50% of 2-methyl-3-hexanol. Okay. Hexanol just means where the double bond, where the OH group is located. And it's 50% and it's 50%. Does everybody see why? Because back here on this carbon, the carbon on the left has one H attached to it. The carbon on the right has one H attached to it. So hydrogen wants to go to one with the most hydrogen, but they're both the same. So you do not have a major and a minor. You have 50% of one and 50% of the other. Is that making sense?
Yes.
All right, perfect. Balanced equation, hydration of the following alkenes. Propene. Propene has 3 carbons, 1 double bond. Okay. So here's where you're going to attack. Okay. The carbon on the left has 2 hydrogens on it. The carbon on the right has 1 hydrogen on it. So you're going to form 2 compounds. One with the H on the left, one with the H on the right. OH on the left, OH on the right. Oh, there it goes. Took a delay there. Okay. So the top one. Okay. Top one is going to be your major, your minor, or 50%. Who wants to guess? Or who
Major.
wants to? That's going to be the major. You got it. It has to be the major, right? Because it's going to attack to the carbon. The hydrogen is going to add to the carbon where there's more hydrogens attached. Hydrogen likes hydrogen. So that's your major product. And it's 2-propanol. Propane means 3. AN means single bond. OL means alcohol. Alcohol is an OH group. And OH group is in the 2 position. Okay. The minor product, okay, is going to be propanol, which is 1-propanol, where the OH group is on the number 1 carbon. Okay, so this is your minor project. This is your major product. Yeah, the major product is going to have the H attached to the leftmost carbon, because there's these 2 other hydrogens attached to it versus 1. So major and minor product. 1,4-dichloro-2-butene. Okay, just basically write it in. We'll do it on the computer so you can see it better. But Butene is 4 carbons. Number 2, there's a double bond. Okay, at 1 and 4, there's chlorine groups on it. And there's your compound. And that's what your compound looks like. Then it's going to attack this double bond. And we're going to put on the double bond, there's going to be an OH and an H. If we switch those, it's the exact same compound, right? Because it's completely symmetrical around that carbon-carbon double bond. So if we switch that, it's still going to be it's 1,4-dichloryl 2-butanol. Okay, it doesn't matter how you range it. Okay, it's going to be the same compound. In other words, we can take this whole compound and just rotate it 3-dimensionally, flip it over, and it's the exact same thing if we switch the H and the OH. Oops, pencil around again. Okay, does that make sense? There is no major,
Yeah.
there is no minor. Perfect. And there's no 50-50 because it's the same compound. No matter where if we switch those two, it's still the same thing. Okay. So you have to understand how things add here for addition reaction. Hydration. Okay, so we're still doing hydration reactions. We're adding water OH to it, H and OH. Okay, so we have CH3, CH. And again, we can open this, we're attacking this double bond. So we're adding an H and an OH. And we can rotate this whole thing, spin it around, and then the OH is going to be on the left-hand side. It's completely symmetrical. So it makes no difference where it's added, it's going to be the same product. So only one product is formed from 2-butene. So 2-butene is going to be the same product when you add water to it, hydration reaction, when we open this double bond up. Because if we add the H here and the OH here, or the OH here and the H here, we get that one compound. Okay. And the name of this is 2-butanol. OLND means alcohol. And it's the OH group is alcohol, and it's at the number 2 position. All right, now you can look at that one. I know it's not symmetrical. Okay. If I look at that, I know there's 2 hydrogens attached to this carbon. I know there's 1 hydrogen attached to this carbon. So if this is carbon A and this is carbon B, where does hydrogen want to attach? A or B?
A.
A, perfect, because there's 2 hydrogens there. So I know I'm going to have a major and a minor product. So I open that bond up and I put an H here, an OH here, OH here, and an H here. And I have 2 products. Okay. So there's my H and my OH. There's my OH and my H. Okay. So which one is the major product, top or bottom?
The top.
Top one. Top was my major product. Okay. Major product, and it's 5-methyl-2-hexanol. And this one is 5-methyl-1-hexene. That's our name of that one. So the major product is 5-methyl-2-hexanol, and the other one is the minor product. Okay, and it's going to be 5-methyl-1-hexanol. Again, we just named where the OH group is, and that's what this OL stands for. And like I said, we haven't got into that yet. We will in the next chapter. Just getting ahead of yourselves here. All right. So asymmetrical or unsymmetrical, okay, is a little more thinking involved. You have to remember the rule, the Kernikhov's principle, that hydrogen likes hydrogen. And you have to think it through how it's going to add. Okay. So this is, let's see, how many carbons? 1, 2, 3, 4, 5, 6, 7 carbons. 7 carbons is hex. Okay. And it's at the 1, 2, 3%. So 3 hexene. So this is 3 hexene. And we're going to do hydration at H and OH. So here's a double bond right here and right here.
It's heptene.
What's that?
It's heptene.
Oh, there's 7?
1, 2,
There's 7.
3.
You're right. There is 7. So it's 3 heptene. I can't count at the end of the day. Seen too many teeth. All right, so 3-heptene, you're right. And then it's attacked the double bond. So there's one hydrogen on this carbon, and there's one hydrogen on this carbon. Okay, so when it attacks a double bond, it's going to be where's the major or minor going to be, or is it going to be 50-50, or is this going to be one product formed? You got 4 choices.
50-50.
50-50, perfect. It's not going to be one product because there's 3 carbons over here and 4 over here. That's asymmetrical. And each one has only 1 hydrogen. So it's going to be 50-50, perfect. Okay, so here's your carbon. This is your double bond. Okay, there's 1 hydrogen here. There's 1 hydrogen here. So like you said, 50-50 is exactly what it's going to be. There's going to be OH here or an H here. Or H here and OH here. We switch them. Okay, so 50% heptene, 50% and 50%. It just matters where the OH group is. It's the only difference. Perfect. So 50-50 on that one. You guys are learning. Good. You guys are getting this really quick. Same thing. Hydration reaction, right? Yeah, hydration reaction, balanced equation. All right. So we're going to H and OH. We draw this thing out, structural formula. Here's the structural formula. There's our CH3, CHCl, CH double bond, CH, CHCl, CH3. So that's what we're drawing out. And if we open this up, we're going to add H here or OH here or OH here and H here. This carbon has 1 hydrogen attached. This carbon has 1 hydrogen attached. So you could think it'd be 50-50. But if you look at it, when you add this, no matter where I add the H and the OH, it's the exact same compound. I can just flip it around and I can just take this end and flip it around over to here, and it's going to become the exact same thing. The OH is going to be on the left. Okay, so it's all single bonds. I can rotate it. I flip it around. It's the exact same compound. So there's only 1 compound formed for this one. Okay, so you have 2,5-dichloro-3-hexene, and you end up with 2,5-dichloro-3-hexanol. OH group at number 3 position. All right, balanced equation for hydration reaction. Hydration means adding water. Here's your double bond you're going to attack. And let's draw it out structural formula wise. Here's 1 carbon. Here's your other carbon. You're going to add an H and an OH, opening up a double bond. You're going to add an OH and an H. All right. Is it going to be a major, minor, 50-50, or 1 compound? Which one of the 4 is it going to be?
Major on top and minor on the bottom.
You got it. Perfect. Major on the top because this hydrogen here is attached to 2 hydrogens. This hydrogen here is attached to a carbon with 1 hydrogen. Okay, so there's your major product. That's 1 pentene. And your minor product. Okay, your major product is 2-pentanol. Again, you name where the OH group is. And the other one is 1-pentanol. You name where the OH group is. Perfect. You guys are getting this pretty quick. Balanced equation here. There's your group. Here's your 1 hydrogen and 2 hydrogens. I can add an H here and an OH here. I can add an OH here, or I can add an H here. Give me different products. Okay. Is there going to be a major, minor, 50-50, or only 1 product?
50-50.
50-50, perfect. Because there's 1 hydrogen here, and there's 1 hydrogen here. It makes no difference where it's going to attach. So it's going to attach 50% of the time to the left side, 50% of the time to the right side. So that's 2-hexene. And this is a 50%. This is 3-hexanol. Again, it's telling where the OH group is by putting OL on the end. And this is 50-50, 2-hexanol. So each one is 50-50 because the same amount of hydrogen is attached to the carbon of each side of the double bond. Okay, let's draw that one out. And this is your compound here. And here's your double bond. These are the hydrogens attached. And Are we going to be 50-50 or major minor or one compound?
Fifty-fifty.
50-50, perfect, you got it. Okay, it's gonna be 50% top one, 50% the bottom one, because there's one hydrogen attached to each carbon. So let's make no difference where it attaches. So let's name this compound on the left here. Let's name what the starting compound is before we added water to it. This is going to be, what's its name of this thing? There's 1, 2, 3, 4, 5, 6 carbons.
Hexene.
So it's hexene. Where's the double bond located at? What number?
4.
You want to give the go the direction to give the double bond the lowest number.
Ah, yes. 2.
2, perfect. It's going to be 2 hexene. Okay. And there's going to be a chlorine and 1 chloro and 5 bromo. Okay, so put all that together. 5 bromo, 1 chloro, 2 hexene. 5 bromo, 1 chloro, 2 hexene. That's the name we started with. Okay. And we're going to go, we said 50-50, 50%, 5 bromo, 1 chloro, 3 hexanol, 50%. And 50% is going to be 5 bromo, 1 chloro, 2 hexanol. Okay. So that one's a 50-50. This one, I think is our last one, is going to be no substituents attached. So we're going to draw it out just like that. CH3, CH2 4 times. So we have 1 hydrogen attached to this one, 1 hydrogen attached to this one. 50-50, major, minor, only one product. What's it have to be here?
50-50.
Got to be 50-50. Perfect. Has to be, right? Because there's only 1 hydrogen attached on both carbons of the double bond. So it doesn't matter which one it attaches to. Okay? And it's going to be different which place it attaches to. It's going to be 50-50. And that's just 2-octene. And it's 50% 3-octanol, 50% 2-octanol. Okay. All right, now hydrohalogenases. We'll do a couple of these and call it a night. All right, so everybody's an expert now on hydration. So we've got halogenation, where we're adding hydrogen. We've got halogenation, where we're adding the halogens. Though they're both symmetrical, so there's only one product formed. And now we got hydration, we're adding water, which is symmetrical, which is unsymmetrical, sorry. And now we got hydrohalogenation, where we're adding like HCl, HBr, a hydrogen plus a halogen. So combined with a hydrogen halide, like HBr, HCl, HF, HI, the reaction is an alkyl halide. It's a carbon hydrogen compound with a halogen. Markonovo's rule is the same thing. Okay. Markovnikov says hydrogen likes hydrogen. Okay. So here's our propene. This is a double bond we're going to attack. This carbon has 2 hydrogens attached to it. This carbon has 1 hydrogen attached to it. So the major product is going to be the one where the hydrogen attaches to the carbon with the most hydrogen. That's going to be the major product. Because remember, we're going to put hydrogen on this side and OH, not OH, but Cl, Br in this case, bromine on this side, or H and Br. So you're going to get 2 products, but the major product is the one where the hydrogen, I've circled the wrong one. I guess they put on the side. Where I get back here, where the hydrogen is on the side with the most, is on the carbon with the most hydrogen, and the bromine is on the one with the least hydrogen. So this is your major product, which is 2-bromopropane, and then your minor product, where the hydrogen does not have the carbon with the most hydrogen, and that's 1-bromopentane. Propane. Okay, so the same rule applies. Same thing, instead of OH, now we're putting Br or CO. That's it. That's the only difference. All the same rules apply. So it's not going to change any of that. And that's called hydrate. That's the review, I guess. Okay. So none of that's going to change. Okay. So we got hydration of alkynes. Now we got triple bonds. Okay. Now this is going to form some tricky stuff here. Okay. This is going to be a lot different than what we've done before because we're not going after the double bond a second time to make the double bond. So here's your triple bond. That's where you're going to attack with water. This is hydration. You get H and OH. Okay. We add H to one side, OH to the other side. When you have an OH group attached to a carbon-carbon double bond, remember oxygen is very what we call electronegative. Oxygen pulls electrons towards it. So what this OH group is going to do is pull the electrons in this double bond to itself and form an alkyl group here. This is called an enol. Okay. And it's going to form either an aldehyde or a ketone. An aldehyde has an H group, a ketone has an R group. Across what this is called a carbonyl group. Okay. So it's going to make an H and then an OH. And if it forms an enol, it's just turned an enol because En is double bond, OL is OH group. That's your alcohol. So En means your double bond, OL means your OH group. When it forms an enol, a double bond carbon, an OH group, the oxygen is so much more electronegative, which means it likes electrons more than carbon. It's going to pull those electrons from the double bond towards itself. And it's going to take this hydrogen and sling it back over here. So it's going to form a double bond of the oxygen, kick that hydrogen off, and then form that new hydrogen over here. So hydration of alkynes is very special. It forms an enol, which forms an aldehyde or a ketone. Okay, so hydration of an alkyne is a more complex process than we talked about before. The initial product is not stable. And again, it's not stable because of high electronegativity of that oxygen atom. Oxygen wants electrons really badly. Okay, that's why we have hydrogen bonding in a lot of biological molecules because of this. DNA, RNA that maintains its structure because of these hydrogen bonds because of the strength of oxygen being electronegative. Okay, the compound it forms as an intermediate step is an enol. Then the enol immediately breaks down by pulling the double bonds from the electrons of double bond into it to make a carbon-oxygen double bond, kicks off the hydrogen and puts it back on the other carbon from the double bond. Okay, so this enol is produced. It's an alkene and an alcohol. It's a combination. So En and OL. And the products rapidly isomerize. Remember an isomer? Same molecular formula, different structural formula. Again, this is the same molecular formula, same amount of carbon, same amount of oxygen, same amount of hydrogen, the same amount of carbons, oxygen, hydrogen here, everything else, but okay, it's a different structure. So it's isomerized. So the final product is going to be either an aldehyde or a ketone. An aldehyde is like CH3COO, has that OO1 carbon and an H. A ketone has CH3COO and another carbon atom. So if this is a carbon group, it's a ketone. If this is an H, it's an aldehyde. That's the difference. So your final product can be an aldehyde or a ketone. And we'll learn how to name those two coming up in one of the chapters. So write a balanced equation, complete hydration of each of the following alkynes. Specify each product is an aldehyde or a ketone. So here's your triple bond. We're going to open up that triple bond. So I'll just kind of do it up here for you first. CH3 goes to C. We're going to open up that triple bond. Okay. And hydration. So OH and an H. Okay. And it could, there's two different ways it could form too. But what's important is this double bond is going to sling up here, and then H is going to come down to here. Okay. So when we add H or OH, we open up our multiple bond right here. And we can put the OH here or the OH here. We can put the H here or the H there. Okay. So there's two different ways we can put the H and the OH. Now, as soon as those are formed, these are enols. Enols are unstable. They isomerize. So this double bond comes up to this oxygen of the OH and kicks it off and forms this carbonyl group here. Okay, this oxygen attacks this double bond. Everybody sees why the electrons don't go this way or don't go this way, because that's carbon hydrogen. It's the electronegativity of the oxygen that wants electrons really bad that's pulling that double bond. So it only pulls in one direction. Okay, it only pulls towards the OH group. Okay, and this is one product formed. This is the other product formed. Is the top product an aldehyde or a ketone? How you determine is this carbonyl group, okay, is attached to an R group. There's R groups on both sides. This one here, there's an R group or a carbon and then a hydrogen. If one of the attachments is a hydrogen and not a carbon, it's an aldehyde. If the both attachments to this carbon, what's called a carbonyl carbon, are carbon atoms, it's a ketone. So there's your enol. There's your ketone. There's your enol group. There's your aldehyde. Kind of made a mess when I drew it. There we go. Get rid of some of those. There you go. Now you can see it. Okay. So does everybody understand that this oxygen here? Let's back up a lot of stuff. The double bond, the electrons are always going to form a double bond here, and they're always going to form a double here. They're going to pull towards that oxygen. They're not going to pull away from it, because oxygen is much more electronegative than carbon. It wants electrons more. Okay. And it's a ketone. If this carbon double bond, it's called a carbonyl group, has two carbons attached to it. It's an aldehyde if this carbonyl group has a carbon and a hydrogen attached to it. If one of the attachments is a hydrogen, then it's an aldehyde.